Over the last couple of days, we've looked at a couple of things regarding thin lenses. First of all, we drew the ray diagrams for every possible scenario of convex and concave or converging and diverging lenses. Then we looked at the mathematics of both converging and diverging lenses. Today we're going to perform a lab that's going to attempt to verify the thin lens equation, which is that 1 over f is equal to 1 over do plus 1 over di equation. The problem is, phrased in the form of a question, is the thin lens equation, that 1 over f is equal to 1 over do plus 1 over di equation, is it valid for a particular thin lens? Now, this isn't going to tell us whether it's valid for every thin lens, right? Okay, we'd have to perform this experiment with multiple lenses to see that. We're going to see today if it's valid for the thin lens that you're using. We have 3 variables, of course, the manipulated, the responding, and then multiple control variables. We're not going to talk about what those are right now. We'll go through the procedure, and then I think they should become self-evident after we've gone through the procedure, what each of the variables are. Material is pretty simple, actually. The materials you're going to use, what we call the optics bench apparatus. The optics bench apparatus consists of a meter stick, consists of a candle, consists of a screen, that's the cardboard, piece of cardboard, and then it contains holders for all of that stuff. The meter stick holders, the candle holder, the screen holder, and it actually has a lens holder as well. The other thing that's present here besides the optics bench apparatus itself is the lens. It's a convex or converging lens. Now, what are we going to do with this? You're going to obtain the apparatus. Everybody's going to get their own, or at least each group is going to get their own optics bench apparatus. And then you're going to need to determine the focal length of that lens using the method that we showed you last week. You're going to focus on a far-off object. Maybe the condo's across the street there. Maybe you're going to walk to the end of the hallway here and focus on something on the other side of the football field. Put the lens at the end of the meter stick and then move the card back and forth until you see a good, sharp, focused image of that object on your card. Now, the distance between the lens and your card at that point when you see the focused image should be your focal length. Because if the object is far enough away, then the rays are parallel to the principal axis and they will converge, come together at the focal point. So, focus on something far off. Wherever you see the image produced on your screen, the distance between the lens and the screen is your focal length. You need to write that down, record that value. That's extremely important because it stays the same. Listen carefully to what I just said. It stays the same through the entire experiment. It doesn't change through the entire experiment, and that's going to be important in a couple of places later on. Once you've got your focal length, you're going to come back into the classroom if you're outside the classroom, classroom or biolab, and you're going to actually perform the meat of the experiment. And it's going to involve changing the distance from the object, which is going to be a candle. We're using a candle as the object because the candle generates its own light. It's bright. We should, every time, see a good, clear, sharp, focused image on the screen because of the brightness of the object. So, put your candle, your object, at the end of the meter stick, put your lens a distance greater than the focal length. You want DO to be greater than the focal length. If your focal length is 10 centimeters, okay, you want your object distance to be 13, 14, 15 centimeters. You want it to be bigger than the focal length. Then you're going to take this screen, this card, and you're going to move it back and forth until you see a sharp focus image. It will not be at the focal length. Because at the focal length the last time, because you were focused on something far off, now you're focusing on something that's a lot closer. So you want to move it around until you see a sharp focused image, and then you want to record that distance. This distance from the lens to the candle, and this distance from the lens to the screen. Write them both down. Write them both down. Now, what should you expect to see for the image? Okay, what are we looking for? Because in the end, the light coming from this candle will go through the lens no matter what, whether it forms an image or not. Whether you have the screen in the right place to see the sharp focused image or not, light will go through the lens. You will see almost every time, no matter where you put the screen, you'll see light on the screen. This is what it's supposed to look like. Right there I see an upside down, sharp, focused flame on the screen. Over here, I see light. Of course there's light. Light's going through the candle. It's just not focusing at that spot. So this is not what you're looking for. This is what you're looking for. It should be obvious to you when you see it. If you're not sure if it's what you're looking for, then it's not what you're looking for. You got that? All right. Record your focal length. Like I said, it should be somewhere in the range, I would think, depending upon your lens, of 10 centimeters to 20 centimeters. Okay, when you're trying to find that focused image from the far-off object, don't be looking at 50 or 60 centimeters. It's not going to be that far. It's going to be somewhere probably between 10 and 20 centimeters. Whatever it is, write it down. Then you want to write down your object distance. Okay, you recorded that in your first trial back here. Okay, whatever DO was, okay, write it down. And then DI, wherever the card was relative to the lens, when you saw the sharp focused image after the first trial, that's going to be your image distance. You're going to repeat that 9 times for a total of 10 trials. 10 different object distances, 10 different image distances. And then, you guessed it, we're going to do something with that. What do you think we're going to do with that? Well, there's usually 2 options at this point. Once we have a data table, we either plot a graph with our data, or we calculate something with our data and then plot a graph. We're going to choose option number 2 today. We don't want to plot a graph of DO versus DI. Rather, we want to calculate the inverse of the object distance. So literally, flip it over. If your object distance was 10 centimeters, then 1 over DO will be 0.1 centimeters to the minus 1. If your object distance was 20 centimeters, then 1 over DO will be 0.05 centimeters to the minus 1. Literally just flip it over. Do the same thing for the image distance, okay, whatever they work out to be as well. Then plot your graph. Your graph will be, and this seems odd, 1 over DI, the inverse of the image distance, or the reciprocal of the image distance, as a function of the reciprocal of the object distance. Note the units here, centimeters to the minus 1. Not centimeters. Okay, that would be DO and DI. It's centimeters to the minus 1, or 1 over centimeters. You should get a straight line here, but it's a straight line that you haven't seen before on any of the activities that we've plotted or that we've performed before. This straight line should look like this. You should see a linear graph, but decreasing in value of 1 over DI. In other words, a negative slope on that linear graph. Let's blow that up a little bit so we get some more space here. There's our linear line again, our decreasing linear line, or our negative slope linear line. Now we're going to do the same thing as we've done for a number of activities now. Let's find the equation for the graph. Let's find an equation from our data sheet. Let's put them together and then see what the significance of some of the things on this graph are. In other words, let's try to find something from this graph. This is a procedure that you're going to go through, I promise you, on your diploma exam. We don't know what the question will be. We don't know what the graph will be. But we know that we're going to see a graph on the diploma exam. It may be this one that we're doing today. It may be one of the ones that we've already done. It may be one that you've never seen before. It doesn't really matter. You're going to go through the exact same analysis as we're about to go through and that we've gone through a number of times already. First thing is, get an equation from your graph. What is the equation for this straight line graph or any other straight line graph, including the one that you will see on your diploma exam? Yeah. Y equals mx plus b. Good. Now what you want to do is replace y with whatever appears on the y-axis. It's 1 over di. Replace m with slope. Replace x with whatever appears on the x-axis. That's 1 over do. Now, usually at this point, we'd say the y-intercept is 0, right? Clearly, it's not here. This is not going through the origin. The y-intercept is something, so we can't drop it. That's okay. It doesn't really make it harder. It just means it's something else that we haven't had before. Now you got to come up with an equation that appears on your data sheet that has the same variables in there. What equation on your data sheet that has both di and do, preferably in the form of 1 over di and 1 over do? Yep. Good. 1 over f is equal to 1 over do plus 1 over di. It's on our data sheet, right? Has the same two variables in it. They're both reciprocals. We can be 100% sure that we got the right equation here. Now we want to rearrange this to take the same form as this one. In other words, solving for 1 over di. So, solving for 1 over di, we're going to say it's 1 over f minus 1 over do. Okay? That's good enough, but my suggestion would be go one step further and take it in the same order as we have our graph equation here. This is 1 over di is equal to 1 over do. Let's just swap places here. Just again so it's in the same order. Becomes negative 1 over do plus 1 over f. Good. Start crossing off things now that appear in both. 1 over di appears in both. 1 over do appears in both. What are we left with? Well, the slope equals what? What's the slope? Yeah. Good. Very good. The slope is negative 1. Listen carefully, guys. We don't even have data yet, but we know what the value of the slope will be. Your slope will be minus 1. Your slope will be minus 1. Your slope will be minus 1. And your slope will be minus 1. Give or take a little bit, right? Theoretically, they all should be minus 1. Experimentally, they'll be off a tiny little bit. Regardless of your data, you should get a slope of minus 1. That's not going to do much for us, right? That's not going to do much for us if we all get the same slope regardless of our data. So what we want to look at is not the slope here, but the y-intercept. What's the value of the y-intercept? Good. The value of the y-intercept, b, is 1 over f, right? We know that the slope is negative 1 because the slope times 1 over do, negative 1 times 1 over do. The y-intercept is 1 over f because it's added to 1 over do on this side, and it's added to 1 over do on this side as well. Rearrange that. Get its value. Get its value. Get the value of the slope, or sorry, of the focal length. Now think about what you've just done. You've got an experimental value for the focal length. You just determined the experimental value for the focal length. At the very beginning of this experiment, you measured the theoretical value of the focal length. 10 centimeters, right? That's what we wrote down, it's 10 centimeters. The years might be a little bit different. With an experimental value and a theoretical value, we can find a percent difference. And the percent difference is the actual minus the theoretical over the theoretical value. The actual value is what we just got. The theoretical value is what it should be, right? What you measured in step 2 of your procedure. Multiply that by 100. Okay, if it works out to be, you guys know what our rule of thumb is, right? If it's less than 10%, then we say, all right, we verified what we wanted to verify. If it's more than 10%, then it's not. Your conclusion, is the thin lens equation valid for a particular converging lens, for the converging lens that you used, yes or no? How do you know? Well, we know based on the percent difference, right? And then finally, your sources of error. We want to have 2 or 3 good sources of error. Now, I'm expecting your data to be very good for this experiment, but as you're going through this, you should also note 2 or 3 good sources of error. Okay, there's a couple of places where you should notice that, hey, like I could be off on this. Having said that, you will still get good data. So don't panic about that, okay? We're going to get what we expect to get here. What do we need to head in? I said problem, but it doesn't really matter about that. I'm not marking the problem because I wrote it down on the pre-lab here. So you're just going to write that down word for word. Okay. I'm only saying the problem because it's always nice to refer back to a problem when you're doing a conclusion, right? Okay, it's not the end of the world. You need the variables. Okay. What did you change? What changed because of that? What had to stay the same throughout the entire experiment? There's at least one thing that's critical as a control variable, okay? If you're missing that, you can't get any marks for control variables. Beyond that, okay, you want that, and then you want 1 or 2 other good control variables, okay, especially that one, though. You want your data, you want your analysis, which includes your data, your analysis table and your graph, you want your conclusion, and then, of course, you want your sources of error.